Today's lesson, we're going to continue section 10.3. We're going to go into the geometric series. And within our geometric series, we're going to find the geometric means. We're going to find the sum of a finite series and the sum of an infinite series. If you remember, we did arithmetic means, and we also did the sum of a finite arithmetic series. Now, we're going to look at that geometrically. So I'm going to recall that an equation for our geometric series is a of n equals a sub 1 times r to the n minus 1. A geometric means is telling us that there's the number of terms between two known terms in a geometric sequence. So if we give you example 1 there, we have 100 and then two spaces and then 0.1 or 1/10. And we're looking for the geometric means between 100 and 1/10. In order to find that, we have to be able to find that common ratio. Well, we know that the nth term is equal to the first term times r to the n minus 1. Setting up that equation, well, we know we have four terms here. This is our first, second, third, and fourth. We know the fourth term, or a sub 4, is 1/10. We also know that the first term was 100. So I can go ahead and find what my common ratio was. And if I know my common ratio, then I can go ahead and fill in my missing terms. So I'm going to have 1/10 is going to equal my first term, 100, times r to the n, well in this case n is 4, since I have four terms, minus 1. So now I have 1/10 equals 100 times r to the third. To simplify this, I'm going to go ahead and divide by 100. So I get 0.001 equals r to the third. Solving for r, I can take the cube root of both sides. So the cubed root of 1/1000 is 1/10. So we know that r equals 1/10, or if you want a decimal, 0.1. So now I can go ahead and figure out what my next values are. I'm going to multiply my first term by the common ratio, 1/10. So 100 times 1/10 gives me 10. 10 times 1/10 gives me 1. And 1 times 1/10 gives me 1/10. Example 2, just another example to help us out here. Here we have 5 terms, our first term being 360, our fifth term being 22.5. We're looking for the second, third, and fourth terms. So here again, we know that 22.5 is going to equal 360 times r to this time the fourth power. Go ahead and divide by 360. Taking 22.5 divided by 360 gives us 0.0625, and that equals r to the fourth. I'm going to take the fourth root of that, and we're going to end up with 0.5 equals r. So I'm taking the fourth root of it. I can also have the plus or negative of that value. So which one is it, or will both work? Well, if I multiply 360 by 1/2, that would give us 180. 180 times 1/2 gives us 90. 90 times 1/2 is 45, and 45 times 1/2 is 22.5. We can also check out the negative. 360 times negative 1/2 is negative 180. Negative 180 divided by negative 1/2 is a positive 90. 90 divided by negative 1/2 is negative 45. And then we get negative 45 divided by negative 1/2, or times 1/2. Negative 1/2 gives us 22.5. So we're going to see that we have two r values that's going to allow us to figure out this geometric means. So we have two sequences that would give us a true statement. a geometric series, we're going to look at the sum of a finite series. And remember, finite is a set number, so it doesn't go on forever. We have two formulas that we're going to work with. We have the summation of any number of terms of a geometric series is equal to the first term times 1 minus our common ratio to the nth power divided by 1 minus r. A variation of this is also a sub 1 minus a of n, or nth term, times our common ratio divided by 1 minus the ratio. Doesn't matter which formula you use, except for maybe sometimes you're given some information that the other one doesn't allow for. And we'll look at both of those examples. So in example 1 here, we want to find the sum of 2, 4, 8, 16, so on and so forth to 256. So I can pick either one of these equations to go ahead and find the sum. I know my first term is 2. I can also go ahead and count pretty easily. I have 2, 3, 4, 5, 6, 7. I have 8 terms. And I know the common ratio, 2 to 4, 4 to 8, is going to be multiplying it by 2. So it's a geometric series. So using my first summation rule, I have the first term, which is 2, times 1 minus our common ratio to the 8th power, since I have 8 terms, over 1 minus 2. Throwing that into the calculator, we have 1 minus 2 to the 8th, and we're going to divide that by negative 1, and times 2 gives us 510. Now if I look at the other equation, we can set this one up as well, since we know the first term, the last term, and the common ratio. So the sum of the 8 terms there gives us our first term minus our last term times the common ratio of 2 over 1 minus 2. In this case, we had 256 times 2, which is 512. 2 minus 512 is negative 510. Divided by negative 1 gives us 510. So notice we get the same answer. Which one do we use? Doesn't matter. Either one of them's on the pretty easy to do. In example 2, we're given sigma notation where we know we start at n equals 2, we go to 11, and our function is 3 times 2 to the n minus 1. We know it's a geometric sequence because we have a ratio to a power, so it is exponential as we look at it. We can find our first term. So our first term is found by plugging 2 in to our equation. So we have 3 times 2 to the 2 minus 1, or 6. 2 minus 1 gives us 1. 2 to the first is 2. 3 times 2 gives us 6. We know the last term. Well, in this case, our last term, remember the number of terms, we take the upper bound minus the lower bound plus 1. So the number of terms is 11 minus 2 plus 1, which gives us 10. So our 10th term of this sequence, we plug in 11. We have 3 times 2 to the 10th. 11 minus 1 gives us 10. And that's going to give us, throw it in the calculator there, 3,072. So now, again, we can use either of these equations. So we know the first term is going to be 6. We know the common ratio. Our common ratio in this case is 2 to the n. We have 10 terms over 1 minus 2. If you want to use the other equation, s of 10 is going to equal our first term, which was 6, minus our 10th term, which is 3,072, times the common ratio of 2 over 1 minus 2. Throwing that into the calculator, we should end up with 6,138. And that gives us our summation of that sigma notation. Example 3, just another problem, very similar to what we've seen before. So we can go ahead and use that equation. We don't need to throw that equation up there. So we know the first term, plugging in 1, we get 20. We know the common ratio is 1/5. And we know the number of terms. 12 minus 1 plus 1 gives us 12. So the sum of those 12 terms is going to equal 20 times 1 minus our r, which is 1/5, to the 12th. And we're going to divide that by 1 minus 1/5. We can throw that into the calculator. We can take our 1/5 and take it to the 12th power. We take 1 minus that value, and we're going to divide it by 1 minus 1/5. 1 minus 1/5 is 4/5, and we get our answer of 1.249999 multiplied by 20, and we get 24.999 repeating, rounded to 3 decimal places, gives us a sum of 25. That brings us into the sum of an infinite geometric series, or a convergent sequence. Remember, a convergent sequence is a sequence that comes upon or draws upon a single value. So it's going to look maybe something like this. To where as we come across, as we go to infinity, this value is getting closer and closer and closer to some other value being convergent. And we know that when we have a ratio that is less than 1, so the absolute value of r is less than 1, then the series is going to be convergent. If that's true, the summation of that infinite series is going to be the first term divided by 1 minus r. So in example 4, we're going to find the sum. If we have 8 plus 4 plus 2 plus 1 plus so on and so forth, the summation is going to equal the first term, which is 8, divided by 1 minus, the common difference here is 1/2. So we take 8 divided by 1/2, which gives us 16. And that's going to be the infinite sum of that. So if we take the values of 8 and we add them to 4, and then we add to 2 and add to 1, as this gets larger and larger and larger, we're looking at the summation of all of those values is going to be 16. Example 5, we end up with a negative ratio. Again, the absolute value of negative 1/3 is 1/3, so that's less than 1. So we can go ahead and use our formula again. Remember, the sum is going to be the a sub 1 over 1 minus r. So here, a sub 1, we got to find that first term. If I plug in 1, 1 minus 1 gives me 0. Anything to the 0 power is 1. So I know my first term is 3. So my summation is going to be 3 divided by 1 minus my r value is that ratio of negative 1/3. So I have 3 divided by 1 minus negative 1/3, or 3 divided by 4/3. And 3 divided by 4/3 gives me 9/4. And that's going to be the summation of those values. The last example I have for today is going to be find the sum of 2, 6, 18, 54. So if we notice 2 to 6, we're going to multiply by 3, 6 to 18, multiply by 3, 18 to 54, we multiply by 3. So we have a geometric series here, but notice my ratio is 3, and the absolute value of 3 is definitely not less than 1. So we know that this sum is not able to be found. We can also say that this sum is going to be infinity. because 2 plus 6 plus 18 plus 54, we're just adding larger and larger numbers together. So that brings us to the end of this topic. I did want to reiterate and go over real quickly what those equations were. Bring my papers back here. So the first equation that we talked about was the geometric sequence formula, where a of n is going to equal the first term times r to the n minus 1. The sum of a finite geometric sequence, we have two of them. Doesn't matter which one we use. The first term times 1 minus r over n to the 1 minus r over 1 minus r, or a sub 1 minus a sub n times r over 1 minus r, and the infinite geometric series, where the sum is the first term divided by 1 minus r. And that's going to end that lesson.